All right, everyone. I think we're going to go ahead and get started here. My name is Bryan Hughes. I am Nebrius everywhere online, like GitHub, Twitter, all that kind of good stuff. And I'm a technical evangelist at Microsoft. I'm also really involved in the Node.js project. I'm on the technical steering committee there, and I'm the chairperson of the community committee. And I've been using TypeScript for about a year and a half now, so I've grown really fond of it, and I've learned a lot of lessons along the way. And so today we're going to talk about using TypeScript in like practical applications. We're going to kind of talk about the language, some of the features it has, but we're also going to spend some time talking about how you integrate it with a lot of other modern web tools as well. Because I found that often is a sticking point for folks. So what is TypeScript? TypeScript is a compiled to JavaScript language created by Microsoft initially. It is an open source project. We have a lot of contributors from outside Microsoft as well, especially coming from Google, since Google manages the Angular project, which uses TypeScript. So in TypeScript, there's a couple of key things that it has. The key thing that TypeScript offers is static typing. And if you haven't heard this term before, what that means is whenever we create a variable, we also give it a type. So whenever we do, var x equals 10, well, x is then considered a number from then on out. Like once a variable has a type associated, that type can never change. So if you were to create, say, for example, var x equals 10, so x is a number, but then you tried to assign a string to it, that is actually considered a syntax error. You actually get a compile time error on this. Whereas if you know in regular JavaScript, this is perfectly acceptable. And then TypeScript builds off this very basic concept and adds a lot of things to the language around that. Specifically, it adds classes and interfaces, and we'll just talk about what that is in a bit. There is a module system in TypeScript. And as I said before, it compiles to just regular old vanilla JavaScript. So you can run it in the browser and in Node.js. So this is what TypeScript looks like. This is a very short kind of method. It takes in a first name and a last name, and it returns a string, a single string that is those two names combined with the space in the middle. If you've never seen this form of string, by the way, see how it has the backtick, that little angled quote, instead of a normal string? This is called a string template that was introduced in ES6, the newest version of JavaScript. Or, well, it's not the newest version anymore, it's about a year out. But it's a fairly new thing and allows us to inject variables into it. Kind of looks like mustache or handlebars if you've used those. So most of this looks like regular JavaScript, but there's a couple of extra pieces to it. Specifically, if you look where we define two variables called first name and last name, with that constant front, you notice that there was a colon after the variable name and then the word string. And so that is how we define types. We have the name, a colon, and then its type. And we can put any type in there we want. So it could be string, number, boolean. And there's some more complex types that you can also assign it, which we'll talk about in a bit. But once first name is declared as a string, like I said, it can only be a string from then on out. And then similarly, if we look at this function definition at the very top for combined names, we notice it takes two arguments, first and last, but they also have a type. We have a colon and then string after first. And so that says first name is a string and will always be a string. And then after our arguments, after that closing parentheses, we have another semicolon and string. That very last type you see is the return type. And so that says that this function is guaranteed to return a string. And if at any point in time we violate these type definitions, let's say combined names decided it didn't want to return anything at all, or it returned a number instead, that actually gives us a compile time error. Meaning we can't actually build our project with these errors in place. TypeScript says, I'm sorry, you have a problem with your code, and you have to fix it first before I will actually build your code for you. So I mentioned more complicated types. One of those complicated types is a thing called an interface. If you've ever used Java or C# or languages like that before, interfaces will probably look pretty familiar. And for those of you who haven't, an interface is like a contract. And specifically in TypeScript, an interface is a contract for an object. We say, okay, we're going to have an object. It conforms to this interface, which means it will have every single property listed in that interface. And it will be of these certain types, and there won't be any extra properties either. So in this example interface, we have 3 properties, first name, last name, and age, and they have specific types associated with them. And then below that, we are creating an object instance, and we use an object literal, and we assign it to the variable fry. But then we also say that fry conforms to this object. So let's say for first name, instead of giving it the value Philip, we instead gave it the value of false. And false is a boolean value, it is not a string. And so that would actually give us a compile time error. Or if, let's say, we didn't have first name in there at all, or we mistyped it and we left off the E on the end, so we had an extra property called first name, and there was no property called first name, TypeScript would actually give us a compile time error. Building off of interfaces is the concept of classes. And classes in TypeScript are based on ECMAScript 6 classes, if you've used those. You see them a lot in React, if you've used React. But TypeScript adds a number of things on top of it. The first thing it adds is the ability to implement an interface, which is what we see here. So we say we have a class ship, and it implements this interface, meaning that the class conforms to that interface contract. Now, there's a little bit of a difference here whenever a class implements an interface compared with the previous slide. On the previous slide with the object literal, if we included a property that was not in the interface, then that would actually be a compile time error. But that's not true with classes. A class can have extra properties in it that are not defined in the interface. And in this example here, you can see we have a name getter, and we have a method called takeoff, and those are defined in the interface. But we also have this property called ship name, and that's not in the interface, and this is perfectly fine. In fact, this is pretty common. If you've ever built classes before, whether using ECMAScript 6 classes or using the old prototype inheritance method, you have probably added some private properties to that class. You know, those underscore prefix variables that you use to store some internal value. And so those are the kind of things you don't want in your interface. The idea with this interface is you can kind of ship it around in your code and other people can use it so they know something about, you know, a class being passed around. But you don't care about those under the hood details. Now, another thing that TypeScript adds is you've probably noticed by now this little public, private thing in front of all the properties. So that's a new thing in TypeScript, and that is what's called basically it's like a property permissions level. If you've ever worked in C++, Java, or C#, you have seen this before. Those exact words come from those other languages. And they specify who is allowed to access that property. If it's public, anyone who has a reference to an instance, you know, if someone has an object instance, they can access that property. And so we think about this as like, you know, what would be documented in an API? The things that are not prefaced with underscores. If it's marked as private, though, this is different. What that means is only the class itself is allowed to access that property. If someone outside of that class tries to reference that property, you get an error. And so historically, those would have been the underscore prefixed variables, you know, the things we don't want people to access. Now, of course, in JavaScript, historically with the underscore, you could still access it. I think we've all done that before. You know, we kind of we had to hack around something, so we accessed in private underscore. But in this case, you're not allowed to do it at all. And it's actually analogous to another new feature in ES6 called symbols. So a symbol in ES6 is a special way of creating a property on an object, but in order to access it, you have to have access to that symbol as well. It's a way of just like hiding internal details, and it's really handy. And if you look at the output of TypeScript, it is actually using symbols under the hood, in fact. So if you see private, you can think of that as using a symbol in ES6. I also mentioned that TypeScript has a module system. Well, in practice, it's actually just the normal JavaScript module system that was defined in ES6. So you've probably seen a lot of this before if you have used ES6 before, you know, through Babel and things like that. So we have, you know, this import statement, which says we're going to import, in this case, an interface from a different file that we call iShip. The one thing that TypeScript adds to the module system over regular ES6, though, is the ability to import an interface. As it turns out, an interface is not actually a value. Whenever you compile TypeScript, the interfaces are actually removed from the code entirely. So that's like sort of just the only addition, but it's really just a small caveat. Other than that, modules in TypeScript are just like ES6. So there's a lot of support for TypeScript in a whole bunch of different editors. Out of the box, Visual Studio, Visual Studio Code, and the JetBrains family of IDEs all support TypeScript. And all of the other major ones support TypeScript through a plugin. So pretty much you can use whatever editor you prefer to use to edit your TypeScript with. So there's a lot of reasons why these things that TypeScript have added are useful. So we're going to talk about that a little bit. The biggest reason is type safety. Like I said, I've said before, everything has a very specific type to it. So if you make a little mistake on that, you're going to learn this at compile time. So let's say, for example, we have an object in it, and while you're referencing a property on it, you have a little typo. You have an A instead of an E or something like that. In normal JavaScript, this will return the value undefined. And if we're really lucky, we will get a crash after that, or something like really obvious. We'll see something is broken, we do a little debugging, and realize, oh, we mistyped this over here, this is undefined. Now, if we're unlucky, it's not going to crash in an obvious way, and we won't notice that we had that typo. Whereas in TypeScript, because this is all clarified ahead of time, if we have a typo in a property name, TypeScript will tell us every single time, and it'll tell us at compile time. We don't even have to run tests or load it up in the browser to see that we have made a typo. And very closely related to this is it reduces refactoring mistakes by a pretty hefty margin. Because in TypeScript, we know all of these objects. We know what properties exist on all objects all the time. Like, this is actually a guaranteed thing. Whenever we want to, say, rename a property on an object, we can do that with complete confidence that we have done it correctly. Because if we did make a mistake somewhere, TypeScript will tell us at compile time. So this is a screenshot from Visual Studio Code. If you haven't heard of Visual Studio Code before, a completely different product from normal Visual Studio. It is based on Electron Shell. It's a pretty lightweight editor. It's very similar to Atom. It runs on all the different platforms, except I think it's got some other features that I personally kind of like more than an Atom. And in this, one of the features it has is the ability to refactor, and it's actually built into the editor. In this case, you can right-click on a property name. You just select Rename. It'll pop open this little text box you can see over here. You type in your new name and hit Enter, and it will automatically rename that property in every single file across your entire project with a single click. And it will do it completely correctly. We have a guarantee that it will rename it correctly in all cases, too. So a refactor goes from something where you're having to grep through your code and you're having to do some tests to make sure you didn't make a mistake, and that's an intensive process, to 2 clicks and you're done. So refactoring gets tremendously simpler with TypeScript compared to regular JavaScript. Now, TypeScript is useful in a lot of cases, but I think there's a couple of areas where these benefits become really important. I would say the first is when you're working in a large team. When you have a lot of people who are working on the same code base at the same time, it can be pretty easy for someone to make a change in one file that affects another file, and someone will make a change in that other file that kind of also goes back. And then you end up with a little bit of collision, and you may not necessarily realize that that mistake had been made. But in the TypeScript case, because these types are all very firmly defined, you're going to surface that collision very, very rapidly, and you'll be able to go talk to the other person and be like, oh, hey, I see you made this change, I made this too. Let's work together to make sure that we fix both of our problems while not colliding with each other. And the TypeScript compiler helps a lot with that, because it's telling you where these things are incompatible. It's also really useful on large projects. If you have large code bases, if you think of mono repos and things like that, and there are a lot of code bases like that, TypeScript really helps out. So I mentioned the refactoring case earlier and how TypeScript can help with refactoring. Well, the thing is, in JavaScript, as your code base grows in size, refactoring gets harder and harder because there's more files you have to search, so there's more code out there. There's just more things you have to double check. So you can think of the difficulty of refactoring in JavaScript is linearly related to the size and complexity of your code base. Whereas with TypeScript, though, because this is all guaranteed, the cost of refactoring is actually a constant. So this is like a big O of n versus big O of 1 kind of comparison. So with refactoring, it just becomes easier. And so large projects especially really benefit from this. Oh, but there's another one as well, and I think this is a really important one. The back-end technology space is changing quite a bit and has been changing over the years. Node.js has been rising a lot in popularity. Ruby also became popular recently. Python is popular. But there's a lot of back-end teams, people who are very experienced and very, very good engineers that come from, Java, C#, ASP.NET, and things like that. And so these people have skills in statically typed languages, and they're not as familiar with JavaScript. And so by using TypeScript instead of JavaScript, it makes it a more familiar place for these kinds of developers to work. They're used to working with statically typed languages. And so it's a much easier transition for these people. All right, so I talked about the type system a little bit. I said there's static types. So I kind of want to talk about the actual type part of this a little more in depth. The first thing to understand about TypeScript is that every type is actually just a native JavaScript type. There are 7 fundamental types in JavaScript as of ES6. Before ES6, there were 6 types. And that is undefined, number, string, boolean, object, function, and symbol. And TypeScript uses exactly those types. Those fundamental types also make up TypeScript. TypeScript did not add any new base types in. So if you come from Java and C#, this will probably look familiar. But there is no integer type or double or any other types that you don't normally have in JavaScript. And so just remember that types in TypeScript are just JavaScript types. We're just making it explicit. And this is also true of classes. So a TypeScript class is actually just a standard JavaScript prototypal class. It doesn't actually work differently. It's just that there's a little different syntactic sugar on top of it. But it's really just the same thing. The second thing about the type system in TypeScript, though, is it is actually opt-in, depending on the settings that you set in the compiler. And so, if you don't have some of the stricter settings enabled for TypeScript, then regular old JavaScript is actually valid TypeScript. And so for types that don't have a specific type assigned to it, TypeScript makes use of this special type called any. And what that means is this variable that has an any type, we can assign any value to it. Which this really means it works just like a normal JavaScript variable. You can assign it a string, and then later you can assign it a number. Now you do lose some of your strictness guarantees. It does increase your chance for bugs, but this is especially handy when you are porting an old code base. What this means is if you have a lot of regular JavaScript and you want to convert it to TypeScript, you can do it a piece at a time. You can go part of a file here and there because TypeScript and regular JavaScript interoperate really closely, and you can mix and match as you see fit. So I mentioned non-inferable types on the last page, and I realize that's a bit of jargon, so I want to talk about that. So what TypeScript does is it tries to infer a type whenever possible. So let's say we have this first line here, const x equals 10. You notice there is no type associated with that. But we know that 10 is a number. This is something that we can guarantee. 10 is a number because, well, 10 is a number. And so TypeScript will look at this and see that, oh, we're assigning a number to x, and so I'm going to go ahead and set the type for you. TypeScript will actually figure out that x is a number, and then it will then still give you errors if you then try to assign a boolean to x. It'll be like, no, x is a number. You assigned the wrong type. And this is really, really nice because it means we don't have to type very much. One of the complaints that I often see for C++ and things like that, I have voiced this complaint, is that you often have to type the same thing over and over and over again. Especially with classes. If you've ever seen C++, let's say you have a class called foo, and you want to create a new copy, you would literally say foo x equals new foo. So you actually type foo twice. It gets a little tedious. And so in TypeScript, you actually don't have to do that very much. And so most TypeScript actually looks like regular old JavaScript. But it actually has all of these static types and all the guarantees around types on top of that, which is really handy. Now, the next big thing is non-TypeScript modules. So TypeScript's pretty great. We have all these types. But any modern JavaScript app is going to have a whole bunch of other dependencies on it. And those are not written in TypeScript. Or they may have been written in TypeScript, but were compiled and converted to regular JavaScript. So what about those? Thinking Express, say, or React, or something like that. Well, TypeScript has this concept called TypeScript Definition Files. And this is a special type of file in which we create this statically defined interface that basically specifies the contract for the external code. It is a declaration of all the types, but there's no actual implementation behind it. So if you've ever worked with C++ before, a TypeScript definition file is basically like a C or C++ header file. And these files have a .d.ts extension. And so this is what a file might look like. We can see we do declare module planet. And so we're saying, we're going to create a module. Here's its name. That name is important for whenever we do resolving like require calls. It's the same thing that you would put in require. And then we say that module exports these functions and these properties. And we have the types. But you notice there is only the type. So we see export function visit and all that, but there's no actual curly braces. There's no code for the function. It's just this type signature. And so by using these, we can use just vanilla off-the-shelf Express, and straight from NPM. But we also have the static type definitions for Express as well. Now, writing these by hand is kind of tedious, and you definitely don't want to have to do that for all of your dependencies. That would just take forever and kind of make it not worth it. So we have a solution for that. And that is what we call global type definition files. In the NPM registry, there is a scope called @types. If you're not familiar with scopes in NPM, NPM has had this for a while. It's the ability to say, I have a package name, and it's a part of like an organization or something like that. And they always look like @types @ something like that for the type scope specifically. Also, if you have an NPM account, you automatically have your own scope as well. So I could publish something as @nebrius/raspberry.io or something like that. But under the specific scope, there are type definition files for thousands of the most popular modules in NPM already. So if you want to use Express, you do npm install Express, and then after that, you run this little command right here. So npm install save dev @types/express. And that's all you need to do. So now in your code, whenever you import Express into your Node.js app, you will automatically have all of the static type definitions for Express. And this is really nice because this will actually tell you if you're calling Express incorrectly. If you forgot to add a parameter to a function call, TypeScript will give you a compile time warning, which is really awesome because you don't have to run your code to realize that you forgot to add that extra parameter. I know this helps me out all the time because I always forget stuff like that. All right, so I've been talking about Node a little bit. We'll talk about a little more in depth how you actually set up TypeScript in practice for Node.js. And don't worry, we'll get to the web right after this too. So the first thing we do is we install TypeScript itself. I always say this as a developer dependency because we don't have to ship this into production. And then we add @types/node. We were just talking about TypeScript definition files. Well, it turns out there is one for Node.js itself too. Also, all of these modules in the types scope are versioned. So if you're using Node.js version 8 versus Node.js version 6, you can install those different versions of this @types/node, and you get all of the API that is specific to that version of Node. So once you've installed those types, then we run the TSC compiler, or the TypeScript compiler, which is called TSC, and then we pass it the init file. In this case, I'm using a program called npx to run that. If you have ever installed a module before without installing it globally, you probably noticed that you can't access any binaries that it comes with, whether this is Webpack or Babel or something else. Well, npm 5 specifically, which is a couple months old now, I think, ships with a new tool called npx. This is written by Kat Marchand, one of the lead CLI developers for npm, and it makes it a lot easier to just run these extra commands. So you can run npx tsc. It's going to look inside the node modules folder, find that binary, and it's going to pass it this -- init command. And whenever we run tsc init, it works just like when we run npm init. It will create a default configuration file for us for TypeScript. And that file is called tsconfig.json. And so in this configuration file, it's pretty similar to the Babel configuration file if you've ever worked with Babel. And we just kind of set some stuff of how we want TypeScript to behave. The first thing we have here is the target. This is the version of JavaScript that we want to target as the output. So this is going to say, do all of the TypeScript compilation, do all those type checks, and then convert it into ES5 compatible code. So this is like a really compatible version of JavaScript. It'll run in Node.js all the way back to, I think, the very first version of Node, in fact. And it'll also work in browsers that go back a long time. It can go back all the way to IE 9. Yeah, so it's really compatible, but we, of course, lose a lot of things. You can also set the target to target ES 2015 or 2016 or something else. The next thing we do is we specify the module system we want to target. So Node.js uses the common JS module format, and so this will take all those import statements and convert them into require statements. But you can also add some others. You can add AMD.js, System.js, and a couple of others if you want. This next part, though, strict true, that's something for TypeScript itself. TypeScript is at version 2.0 now, or well, I think it's like 2.2 or 2.3. But when 2.0 was released, there was a lot of really big changes in TypeScript. It actually includes a lot of really new, stricter type checking, which I find to be really useful when I'm writing new code. It just helps you to find out errors sooner. But there was a lot of legacy TypeScript out there. And so if you set strict to false, it will act like the TypeScript 1 compiler. You won't have as many checks, but it will be compatible with your old code base. So that's all that's doing. And finally, we are saying where we want to put our compiled code. In this case, it's into a folder called dist. And then finally, we say we want to have source maps. And then the next part below that, that specifies the files that we actually want to compile. And we're using glob patterns here. So once we have our configuration file and we have our dependencies installed, then we can compile code. And in the Node.js case, what it'll do is it'll take every TypeScript file, which has a .ts extension, and we'll generate an equivalent JS file in that same folder structure inside of dist. So it's like a one-to-one transformation from a TypeScript file to a JavaScript file, which in Node.js is what we want, because Node.js is always going to be a collection of a whole bunch of files. The web is different, which we will talk about here in a second, though. Before we talk about the web, though, another thing that most people want is a linter file. We have JavaScript checks. The JavaScript engine itself will tell you if you have a syntax error in your JavaScript, but we usually want to know more about that. And so we oftentimes will use a linter. ESLint is probably the most popular, I think, right now for regular JavaScript. And TSLint is built to be very, very similar to ESLint. They even share a lot of the same rule names. Except that TSLint is meant for TypeScript, and it has a couple of TypeScript-specific parts to it. So we install it, once again, just npm install save dev tslint, and then we initialize it, the same way we initialize tsc as well. And when we run tsclint init, that will create a default configuration file. Now, this is not the default configuration file. The default configuration file actually has a whole bunch of rules that are commented out with comments explaining what they do, which is really awesome, but I'd have to stretch it across like 5 slides, and I don't think you wanted to see that. So this one's a little more compact, but we can still talk about it. So the first section, default severity, that specifies what happens when we encounter an error. So if there's like a TypeScript error in the code, when we specify error, that means it's going to print the error and it's going to stop running. It will prevent it from building. But you can actually lower that, and you can say, well, there's an error here, but I want to build the code anyways. There are times you want to do that if you're like rapidly iterating and prototyping. The next section, extends. This is the ability to take some other tslint configuration file, and we say we're going to extend it. And there's a couple that are built into tslint. This one specifically is called tslint recommended. And that specifies a number of certain just like style elements. And that really helps a lot, because the tslint recommended has, I think, 40 rules defined in it. Same thing in ESLint. If you've ever looked at a stock ESLint file without extending anything, it's that long and kind of tricky to maintain. So this helps a lot with that. Then we have 2 separate sections here called JS rules and rules. I mentioned before that JavaScript and TypeScript are interop really clearly. So tslint can actually check JS files as well as TS files. And so the JS rules section is the linter rules that we want for JavaScript files. This is really nice because that way we don't have to configure both tslint and ESLint to work on the same code base if we happen to mix and match files. And then the rules section, which has some options that I'm sure are not contentious whatsoever, is where we specify our TypeScript linter rules as well. And then finally, rules directory is where it searches for things to extend as well. All right, so I mentioned Node.js. Now let's talk about React. So this one is a little more complicated case. Front-end code typically has a more complicated build step. So first, what the code itself looks like. This is a little bit of example React code written in TypeScript. For the most part, it looks like regular TypeScript code. So we're importing another view that we're going to incorporate. We're importing React itself. We're declaring a class called container view that extends the React.component. This is the same thing that you do in normal ES6. There's a render method. You can see there's actual JSX syntax in here mixed with the TypeScript syntax. And yeah, so for the most part, it's pretty typical React code, but I'm sure you're noticing there's a couple of extra details that are added. So first, we have an interface at the top called container props. This interface specifies all of the props in this React component, the things that are under this .props. This is really nice, actually, because this allows us to give static types for all of our properties. And we don't have to use the other mechanism that React uses for validating props. That mechanism, if you've used it, you can specify an object on your class, and you say these are the various options and these are their types. But that's actually a runtime check. There's a very slight runtime cost associated with it. Whereas in the TypeScript case, this does the exact same thing, except it does it using interfaces and it's a compile time. So like all of this type checking isn't in your actual code when you're running it in the browser. Now, there's another little thing you might have noticed. You see where container view extends React.component, and then there's that angle bracket after it. So that is the part where we are telling TypeScript what the properties for this specific React component are. And in general, that thing that we're seeing with the little angle brackets is a concept that is called generics. If you've ever used Java or C#, they also have generics that looks the same way. And if you've used C++, they actually have the same thing too, except instead of calling it generics, they call it templates. So if you've ever done C++ templating before, this is basically the same thing. And so what a generic is we create a class or a function or something like that that takes in some parameters. And we say, okay, there's this parameter, it has some type, but I actually don't know what it is. So I'm going to create a placeholder. We're going to just make up a type. We'll call it, say, T or whatever we want. T is pretty common. And we sort of use this temporary placeholder inside of all of the class code. And then where that type gets specified is the person who consumes the class. So in this case, we're saying, okay, we're going to use React.component, and here is that type that you have a placeholder for. And then once you provide that type to it, the TypeScript compiler can then go and check the whole React class, like all of that code base, to make sure this type you supplied it works. A little bit confusing, I know. But just think of it, in this case, we can talk about the specific case, because I think this is actually a really good usage of it. So every React component has a property called this.props. Now, what is in that specific property? We know it's an object. It's always an object in React. But other than that, what goes into it actually changes from React component to React component. And so we're saying at the base level, at the React.component level, that is defined using a generic. We're saying we have this.props property, but we don't know what goes in it because someone else is going to define it. And so the person who defines it is actually container view right here. We're telling the React that, okay, this.props property has a definition, and here it is. And so this is really cool, because if you look in the render method, you see we access this.props.items.map. This.items is an array. It's an array of strings. Because we have supplied this generic, the generic React.component thing with an interface, we can say, oh, this.props now conforms to this interface. And we know that items is an array. And so we actually have strict type checking on that. So if we did, instead of items.map, we did, let's see, what's a good one? This.toFixed, which is something that's on the number prototype, but I don't think is on the array prototype. Please correct me if I'm wrong. We would actually get a compile time error. We would say, this doesn't exist. TypeScript actually knows that this.props.items is an array. So we continue to get this really strict type checking, even on this thing that varies from component to component, which is really, really handy. Now, how do we set up this build pipeline? It's kind of complex. So first, you install all of that stuff. The very first one installs React in React DOM, which is pretty typical for any React application. By the way, I'm assuming npm 5 for all of this. In npm version 5, which, like I said, is very new, whenever you install a package, it will automatically save it. So the -- save was not necessary in this case. However, if you're using npm version 4 or older, add -- save after install, and it will do the same thing. Then after that, we have a number of developer dependencies. So in that second command, we are installing Webpack itself, and we're also installing TypeScript. And these are like the core build tools. The line after that, we are installing 2 loaders. If you haven't worked with Webpack before, Webpack is a very powerful build system. It allows you to take a large code base, that is typically a front-end code base, lots of JavaScript files, you might have HTML files, CSS files, JSON, all sorts of different components, and it will compile that down to a single JavaScript file that you can ship off to the client. And it figures out like all your require calls and maps it all together. It's a great tool, but it's also pretty tricky to use. The way they've made it really flexible, though, is they have the ability to add plugins to it that handle specific use cases. And they call these plugins loaders. So we are installing 2 of these plugins. The first one is called Awesome TypeScript Loader. There are a couple of loaders out there for doing TypeScript. This one I think is the best, and this is the one that Microsoft recommends you use at this point in time. And then the next one we're installing is called Source Map Loader. So Source Map Loader is really important for debugging your code. Whenever you have your web page loaded up in Chrome, you have your Chrome DevTools open, you don't want to have to debug the compiled JavaScript. If nothing else, it's because it's one file that is probably 15,000 lines long. That's kind of a pain. What you want to do is debug the original TypeScript files, even if you're running the compiled JavaScript. And so a source map is a map that basically it maps those changes out. It will say that this line in this column in your compiled code maps back to this line in this column in this file in your TypeScript. And so the Chrome DevTools, if we set up our source maps correctly, will actually allow you to set breakpoints in your TypeScript code, which is really great. And then on that last line, there are 2 more things we install, and these are the type definition files, like we saw earlier, for both React and React DOM. So once we have installed all of those dependencies, we are ready to configure Webpack. So here's the first half of the Webpack configuration. If you've worked with Webpack before, its configuration can be kind of long and a little involved. So the very first line, we have entry. Every single Webpack compiled object will have an entry point. And what this entry point is this is the very first JavaScript file that you run in your application. And every other file needs to be called either directly or indirectly from this first file called the entry point. So we're specifying that one. We could call it, say, source index.tsx or tsx. So just like in JavaScript, whenever you're doing JSX with React, you add that x at the end. We call them .jsx files. Same thing here, except we just call them .tsx files. The next little bit called output, we're saying the directory that we want to put the compiled output into and the name of the file. Now, with Webpack, you can actually get a lot more complex for both of these that support some other use cases. If you need to, substitute that here. But this is a basic example that will definitely get you up and running. The next thing we do is there's this dev tool source map. Now, you only want to do this on development code, but it changes the way Webpack loads code. It makes it easier to debug. We can talk about that later if you know more details. Just know that you probably want that for your development builds. And then the last thing is resolve. So what resolve does is it tells Webpack what types of files to look for in your code base. It doesn't look at every single possible file that might be in there. It only looks at certain types. By default, it only looks at .js files. So I usually like to add .json as well, because sometimes I require JSON. But then for TypeScript, we have to add the .ts and the .tsx files. So that tells Webpack, these are files that we are interested in. Make sure you go ahead and process them, and you run them through the appropriate plugins. So that brings us to the next part of our Webpack config. Right here, we have a module section. That section defines how we process each module, which is typically a single file that has import and export syntax in it. And we have a list of rules, and those rules are where we specify the plugins for TypeScript. And so we're saying use the awesome TypeScript loader and the source map loader. There's a couple of fiddly bits here, the enforce pre, all of that, just know that those are things necessary to get this to work correctly. Once you have this Webpack thing in place, you can have your whole React code base. It will compile down to a single JavaScript file. You load it in your browser, and then you can debug your TypeScript and JSX directly in Chrome. So one last little consideration whenever you're doing this is that the TypeScript compiler is a little bit different than the Babel compiler if you've used it. TypeScript does not ship with a runtime, whereas Babel does. If you've ever seen the Babel-runtime, TypeScript does not have an equivalent. This is a design decision that the developers made. What this means is that the newer syntax for ES 2015 is handled by the compiler, as well as all the TypeScript stuff itself, but the newer runtime stuff is not. So in other words, TypeScript does not ship with a polyfill for things like object.assign, symbol, and things like that. So if this is something that you are concerned about, that you want to target older browsers but use this newer runtime stuff, the way we recommend doing that is you compile your TypeScript to ES 2017 format. It's 2017 right now. Next year, replace that 7 with an 8. And then pass it through Babel and have Babel compile it down to ES5, and you conclude the runtime. And that way you get the TypeScript code along with the Babel runtime, and everyone is happy. And if you want to learn more about TypeScript, go to typescriptlang.org. And thank you, everyone, for listening in.